Hello, everyone. Can you guys hear me? Yeah. Welcome to our talk. My name is Kurosh. I'm a tech lead in the AI team here at Anyscale, and together with Arthur, we're going to be talking about some of the lessons we learned from fine-tuning Llama-2. I hope these insights that we uncover in this talk will be of help to you as well. So here's the outline of the talk. I'm going to start by motivating the promise behind open source LLMs and why specifically we need to fine-tune them. I'm going to briefly talk about how Ray Train fits into picture when it comes to LLM distributed training. And then we're going to cover some learnings around fine-tuning problem setup and parameter efficient fine-tuning. So since the emergence of ChatGPT, we've seen two major separations in industry trends. On one hand, we have closed source language models. This includes models like GPT-4 or Claude-2 from Anthropic. These kind of serve as a very powerful general purpose assistant model that is capable of solving a wide variety of tasks. But one of the kind of like things that are on top of mind of people is that they're prohibitively expensive to run in production. And also, more importantly, there's a lot of ambiguity around data governance and how your data is getting used when you're using these systems. At the same time, we have open language models. This includes models like Llama-2 from Meta or Falcon models or Mosaic MPT models. They kind of have promises on the other side of this spectrum, which is they're often smaller and cheaper to run. And more importantly, they give you more control over your data and your technology stack in serving them. What is more interesting is that in recent months, we've seen an immense progress on the open language models, closing the gap compared to proprietary models like GPT-4. This is a leaderboard from LMSys, kind of an organization at UC Berkeley, which kind of keeps track of the progress that is made on language models by evaluating these models across a wide range of kind of tasks and then puts them on this leaderboard. Llama-2 models have come very close to kind of like GPT 3.5 and other proprietary models. But one of the kind of problems that exists like in these language models, you can categorize them into two subsets. They're often like when these models produce like completions, what they output is oftentimes not factually grounded. They often hallucinate and make things up. And there's another category of problems, which is they often don't follow the format that you have in your mind or like intend to use these language models for. This figure kind of shows a spectrum of techniques that kind of try to address these two types of problems. On the bottom, we've got prompt tuning or prompt engineering, and then few-shot prompting. We have fine-tuning, which addresses following a form problem. And then we've got retrieval-assisted generation, which explicitly addresses the hallucination. And on top, we've got reinforcement learning and training from scratch, which are kind of like more complex and only available to a few companies. Today, we're going to talk about fine-tuning and how it addresses the form problems with these language models. So why fine-tune language models? In the next few slides, I'm going to cover a few reasons that shows the benefits of fine-tuned language models. First thing to point out is few-shot prompting is a technique that enables in-context learning, meaning that we found that like you can, in language models, you can provide a few examples of desired input-outputs and feed them into the context of these language models as input and have the model generalize that same pattern matching to unseen data points. But there are often many times that your data is huge and doesn't fit the limited context window that these language models provide. So in this case, in these scenarios, what you can do is instead of putting these examples into the context, bake them into the neural network weights that essentially present the internal knowledge of these language models. Another reason to think about fine-tuning is there are a lot of tasks that are hard to describe in words. Some of these like subtleties go around like formatting out the output, a specific output format that you have in mind, or having the model generate something in a specific tone. You may attempt to fix these by prompting with phrases like output this thing in this JSON format, or like put something like the final answer in this integer format that I want to parse later in my software. But there are often many times that language models don't respect these kind of like phrases, and you may need to provide several examples to kind of reinforce what you mean. In the following a specific tone, another example is like you may say something like, hey, write this in a concise, respectful, or helpful manner without being explicit what these kind of words mean. And you may need to, again, provide some examples what these words mean for the model. So with fine-tuning, we can actually leverage a lot of illustrations and bake that into the internal knowledge of the model. It can also save you tokens. There are many applications that you can get away with prompt engineering, but oftentimes this prompt ends up being too wordy or verbose with many examples. But the thing that you have to keep in mind is if you want to run this in production, for every single request and every output token that you want to generate, you have to feed in the same context scene, and you're going to have to perform computation on it. So if you have cases where this is too verbose, it's going to actually incur a lot of cost during deployment. With fine-tuning, you can kind of implicitly bake this prompt again into the knowledge of the network and get away with like a cheaper serving cost. And last but not least, as we show later in the talk, with fine-tuning, you can oftentimes get a faster, cheaper model at the same quality for some of the niche tasks compared to, let's say, larger models or even GPT-4 in some cases. So this is a plot that I think you guys have seen already in the keynotes and other talks here, which kind of demonstrates an example of what we mean by niche tasks, like a SQL data generation, how we can fine-tune these small models to kind of outperform other powerful models for this specific task. We're going to cover more of the experimentation side later in the talk. Now I want to just highlight and briefly talk about how Ray kind of fits into this picture. There's a great talk that was presented by Yunshuan yesterday that dives deeper into how Ray Train is a production-ready library for distributed deep learning. I'm not going to cover as much details, but I'm going to just highlight some of the features that makes Ray Train great for this type of workload. So what is Ray Train? Ray Train, in my opinion, is the best framework for orchestrating multi-process training workload, and here is why. First of all, it provides a very simple API, 100% Pythonic, that you can take existing Python code in your favorite framework and just integrate it with Ray Train to distribute it across your cluster. Plus, it has also seamless integration with other libraries in the Ray ecosystem, like Ray Data, that provides distributed data ingestion, which can be very helpful when you're dealing with large data sets. It provides tools around faster development. For example, it automatically sets up distributed environments so that these lower-level libraries like CUDA, Nickel, these things can communicate to each other. And as an ML developer, you don't have to think about them and just can focus on your model training and loss curves and things like that. Another way to look at Ray Train is that it is a simple and elegant job scheduling with features like auto-scaling or support for heterogeneous resources. You can actually survive in today's world where like GPUs are very scarce and there's like capacity issues at reservation. You can put together heterogeneous clusters and get unblocked when you're training something in development. And last but not least, there's a lot of observability tools built around Ray that helps us like easily debug distributed applications and unblock ourselves. Yeah, so now that we talked about kind of the infrastructure side and why we should do fine-tuning, let's talk about what it takes to do fine-tuning. How do we set up problems for fine-tuning language models? So there are two main pillars that you have to think about very carefully when you want to set up a fine-tuning problem. Obviously, there is data collection and formatting, and I want to really highlight the importance of evaluation. So to crystallize these things into concrete examples, we're going to use this natural language to SQL query generation. So data set quality is crucial. I think you've heard it already from even Adobe's talk here. In generative AI, data set is kind of the king, and you have to invest a lot of time in it to make sure you've got high-quality, curated data that captures your intention of how these language models should behave. So in SQL generation, examples are formatted like this. You have like a natural language statement that poses a question about a data set, and there is like a table schema presented by a bunch of tables, and then like variable names and what data type they have, and then at the end, a desired query that you want these models to generate. It's very important to make sure these data sets are clean. For this type of a study, we did a lot of data curation, manually went through all these data sets, make sure, kind of understood what are the common errors in the data set, fixed them, filtered them, to make sure, for example, table names make sense, they represent what the underlying data is. Data types match, for example, the query that is generated. So to get these good results, you gotta curate your data. And I can't emphasize it enough, just by one like slides. Next thing that you have to think about the data is, and this is kind of an important one, is the way that you kind of format them during training is gonna impact how you want to use them, like ask the model to do something. So training and inference data format should be very consistent with each other. So I'm going to give you an example in this SQL generation. Imagine my training data set. I structure all my examples like this. Write a SQL query to answer this question based on a table schema, followed by 2 new line symbols, context, 2 new line again symbols, and then the question. And then have the model learn how to output the kind of corresponding query. I go ahead and train a model with this, but at inference time, I come back and ask the model the same question, but in a different format. Like, here is a database, maybe I don't specify the schema, and then I ask it, hey, convert the following to a SQL command, like show names, blah, blah. And then when I see what the model produces, it's kind of like wrong in subtle senses. Like, it, for example, forgets the name of the schema, or it doesn't do this order by like descending. But the reason behind like this thing is that you have to think about how the model has seen the data before. It has only seen the data in this particular format, and then you're throwing it at it like a new kind of format of data, which kind of gets to convert to new symbols that this model may not even recognize and may not generalize very well to. So it's very important to kind of have a consistent format when you're actually running inference on training on these models. Or if you want to have variations in the type of like data that goes into inference, you have to have the same type of variation in your data as well. So these models learn to be robust to those type of variations. And now I want to talk about a little bit about setting up evaluation pipelines. This example is kind of very specific to the SQL generation, but it kind of inspires other ways to think about it. So let's talk about SQL. So SQL, like your model outputs something, like select blah, and then you have a reference output that you want to check whether what model generated is equivalent to. There are cases, this is a contrived example, but this kind of greatly captures the nuances behind this task. It's very complicated to ensure whether what the model outputted is consistent or the same as the reference output. You cannot do character for character matching. You cannot do more complex methods like abstract syntax tree matching. Maybe you have like expressions, math expressions that are equivalent but look different. Then this AST matching method would also not work out well. What we did here was to use GPT-4, actually a powerful model. Although it costs, and it can become expensive, you're doing an evaluation pipeline. So it's like a one-time cost that you can pay up front to set up evaluation pipelines that you kind of keep consistent throughout your experimentation. So what we did here was we asked GPT-4 to create a bunch of mock tables where, like, conditioned on, for example, the reference output and the table schema, where if we ran the reference output against, we could check what got what came out as a result of running that query would match the same thing that would come out as running the model output against the same mock table. So by doing so, we kind of curated and handcrafted maybe like 200, 300 examples of such unit tests where we could like run all of our experimentations against and make sure we've got like consistent evaluation pipeline in a scalable way when we are experimenting with these like fine-tuning tasks. So the takeaway from this is that there are tasks out there that you may want to apply fine-tuning to that creating an evaluation may be a hard thing to do, but you can leverage these like more powerful models to kind of automate that part and take some of the human effort out of the loop. Now let's talk about some of the learnings we had from running these experiments on Llama-2 models. So this plot was kind of shown in the keynote as well. We have applied fine-tuning to kind of several tasks that we thought might be relevant to what other people might want to do with these language models. I already talked about the SQL generation task in details in the middle. That's what's shown in the middle. On the left side, we have functional representation, which is just a task where you have like a unstructured text asking a question or like have a comment about something, and then your task is to read that text and convert it to structured data. This is a very common task that in like health space where, for example, doctors write a lot of notes and you have to kind of parse that and extract it in a structured format. And so that's basically what is shown here. And we've got another task which is more geared toward mathematical reasoning and logical reasoning. GSM-8K is a data set of around 8,000 examples of basic math questions, followed by some answer, and you want to evaluate whether language models can solve this type of task. So what is shown here is that these darker bars are the performance and success rate of these like models, the chat fine-tuned models right out of the box. So you don't do any specialized fine-tuning on them. And they, compared to GPT-4, for example, they do very poorly. They're not even close to the performance. But if you kind of use the training data that is curated for these tasks and then fine-tune these models and then do the evaluation again, you'll see that the performance gets boosted so much that it can actually beat GPT-4 in these two kind of tasks. However, in some of the tasks that involve more things than just following a format, right? Math requires more understanding of like reasoning and logic, piecing together different things about the logic behind the question. And although fine-tuning can help get you from, let's say, I don't know, 40% to 50%, it is still far behind kind of performance of more powerful and general purpose models like GPT-4. What this kind of presents is the opportunity for applying fine-tuning on these form-following tasks, like this functional representation or SQL generation, are the kind of tasks that the model does not have to really kind of understand the world or how the world functions. They just have to learn how to map like a certain format of input to another format in the output. And this is where like fine-tuning can really help. Now I'm going to hand it off to Arthur to talk about learnings from parameter-efficient fine-tuning.
Right. Thanks, Kourosh. Hello, everyone. All right, so now that we have seen the value of these models, let's talk about parameter-efficient fine-tuning. So first of all, what is parameter-efficient fine-tuning? In full parameter fine-tuning, what you do is just a continuation of the training, but on specialized data. And parameter-efficient fine-tuning is the same thing, but you're only fine-tuning a small number of parameters. So this could be a subset of the parameters of the original model, or it could be some additional parameters. The point being that it has to be very few parameters. And there's a couple of techniques that exist out there to do this. And one of these techniques is LoRA. So LoRA means low-rank adaptation of LLMs. And you see here on the left side a kind of schematic of the internals of a transformer. And on the right side here, you see how LoRA works in principle. So for any given layer from the transformer that is dense, so for example, like a feed-forward layer, you can grab that layer and you can apply LoRA to it. So what does that mean? Well, you have these pre-trained weights. And what you do during training with LoRA is you freeze them and you set them aside, and this will become quite important later. So you set those you freeze them and you set them aside, and then you add an additional matrix, A times B, that can be decomposed into two low-rank matrices, A and B. And these two matrices combined have very few parameters compared to the original parameters, the pre-trained weights that you would normally be fine-tuning. So this is really where the trick is here, and this can bring you two things. First of all, during training, obviously there's a much smaller optimizer state to be kept in memory. And then second of all, you're left with much smaller checkpoints. And we'll talk more about this later, but let's first talk a little bit more about the quality of the models that we gained out of fine-tuning with LoRA. Right, so this should look somewhat familiar. These are the same tasks that Kourosh talked about earlier. So we have the functional representation task, SQL generation, and the math task. And we added another shade here, a medium shade, to the dark shade that signifies the baseline, and the light shade that signifies how well full parameter fine-tuning does. So we added the medium shade here to signify how well LoRA does. And you can see for the left two tasks, for functional representation and SQL generation, that LoRA did basically almost as well as full parameter fine-tuning. So the relative difference in accuracy here is like 1 or 2%. And we can learn from this already that with LoRA, we're able to solve some like real-world problems very well, actually better than what we got out of GPT-4. And but on the right side, you see the math task again, where LoRA is lacking a little bit behind. So for the 13 and 70B parameter models, we're seeing differences of like 2 or 3%. And for the 7 billion parameter model, the lack in quality was even greater. And our hypothesis around why this might be is that like math is generally hard for LLMs to do, as we know. And then LoRA is also a more difficult optimization task. So since you have much fewer parameters to play with, the optimization landscape is a little more tricky, and this might just add up. So something we can maybe learn from this, and this has to be seen like in future tasks that we look at, is that the performance of LoRA might depend a little bit on the type of task that you're looking at. Right, so another thing that we learned with LoRA was that it's sensitive to the learning rate. So with full parameter fine-tuning, what you'll find generally is that it's very stable across a wide range of learning rates. And when we used LoRA, we encountered some instabilities here. So a learning rate that you'll see widely used on the internet is 1e minus 4, and we used that at first as well, and then ran into some of these instabilities. And you can see here how just by tweaking the learning rate a little bit, we got a much smoother learning curve here, this purple one. Yeah, and then another thing that we did to improve stability was, interestingly, prompting. So what you can do during training, and obviously you have to do the same thing during evaluation, as Kourosh said, is you can apply some prompt engineering basically during fine-tuning. So you create some helpful context for the model, like for example, you're a helpful assistant. This is like a SQL table and a query and stuff like that. and then you prepend that to what you're normally inputting to your model. And what that leaves you with, if you, like, we fixed everything else here, like seeding and learning rate and everything, right? But what that left us with was even smoother learning curve here, the orange one. Yeah. Cool. So now that we've talked about like how well LoRA does on these problems, and that we just might have to tweak it a little bit here and there, let's look at the upsides of LoRA. So first of all, as I said in the beginning, the optimizer state is much smaller, right? So for the 7 billion parameter model, for example, that we fine-tuned, we were able to fine-tune the 7 billion parameter model on a single AWS P4DE 24x large instance, and we were simply not able to do the same thing with full parameter fine-tuning. And the other thing is, as you can see here, the checkpoint sizes are much smaller. So with our LoRA settings, we were left with checkpoints that were like 40 megabytes for the 7 billion parameter model and 12.6 gigabytes for the full parameter fine-tuning. So obviously, with full parameter fine-tuning, every time you checkpoint, you have to checkpoint the entire thing, right? With LoRA, you're just checkpointing these two matrices, A and B. Cool. So this brings us to our sixth learning. So as I said in the beginning, during training, you freeze these weights, right? And you set them aside, and you add these two matrices, A and B, that are your LoRA weights. And what this means during serving is that you take those frozen weights, like the original model, and you put it in memory. And then along with that, you have an array of LoRA weights that are task-specific. So this ties in very well with what Kurosh said initially about in order to beat these open and large and general purpose and very expensive models, we need to find small models that we fine-tune on like niche-specific tasks. So you can imagine like one set of LoRA weights per task here. Right. So what have we learned about LoRA now in terms of a trade-off? First of all, if your sole concern is model quality, there's no way around full parameter fine-tuning still. You'll still have this edge of 1 or 2 or 3% of relative accuracy. The training time between the two, the difference in training time is really not there. So initially we thought like LoRA must be much quicker, like fewer parameters, fewer things to checkpoint, stuff like that. But it turns out that if you look at the time it takes the model to converge, as in like wall clock time to a given perplexity, it's roughly the same between the two methods. And then what we really gain from LoRA is, first of all, the memory footprint that can really unblock you on using smaller instance types in training. And second of all, the serving efficiency that's just greatly enhanced. Right, so here are all the learnings that we mentioned today. First of all, dataset quality is crucial. Training and inference data format consistency is crucial. And we use GPT-4 to set up a reliable evaluation pipeline. Then LoRA being sensitive to the learning rate, and prompting datasets help with training stability. And lastly, that LoRA's big advantage is really the serving efficiency. Yeah, so one more thing here. There is another talk about these LLMs in production by our chief scientist, Walid, and that's going to be at 3:15 p.m. in Gate Ballroom B. Cool. Thanks, everyone, for attending.